Hello students, in this video lecture I will cover up fragmentation and paging in memory. First we will cover up the memory fragmentation. As processes are loaded and removed from the memory, the free memory space is broken into the little pieces. These memory space are known as the holes. It happens after some time the process cannot be allocated to the memory blocks due to the small size of memory blocks, and these blocks cannot be used further. For example, suppose that this is the memory and here is the OS. Now I have three partition in which process P1, P2 and P3 are residing, and this memory space has 200 MB space, 300 MB space and 400 MB space. So when the process get completed, P1 process get completes, it's removes from the memory, and there is a there is a space that is the whole of 200 MB. And at the same time, just after the P1 P3 leaves the memory, and there is a whole of 400 MB. Now a new process comes that requires only the 100 MB, so we will allocate process P4 in this slot, and then after a new process P5 comes that requires only the 150 MB. It requires 100 MB. So here is a whole of 100 MB remains, and here is whole of 250 MB. So total we have 400 MB available, but when a new process arrives that requires 300 MB, 300 MB, so we cannot allocate that process into memory. Why? Because we have the space, but that space is not continuous. 100 MB space is here and 250 MB space is here, but this space is not continuous, so we cannot allocate this space to any process. So this space is known as the fragments, and this process is technique is known as the fragmentation. So fragmentation is of two types: internal fragmentation and external fragmentation. Firstly, I am going to discuss about the internal fragmentation. In this fragmentation, the process is allocated to the memory block of size more than the size of that process. What does it means? I am again repeating. In this fragmentation, the process is allocating a memory block of size more than the size of the process. That means the block size is larger than the size of the process. So process can accommodate in this. Due to this, some part of the memory is left unused. This is the part which is left unused, and this causes internal fragmentation. And this causes the internal fragmentation. It should be noted that internal fragmentation occurs when fixed size memory blocks are allocated to the process. Always. That means in the fixed allocation, internal memory fragmentation is possible, not in case of the dynamic. Second one is the external memory fragmentation. External memory fragmentation happens when there is a sufficient quantity of the area within the memory to satisfy the memory request of a process. However, the process request cannot be fulfilled. This is due to the memory space is not continuous. Either you apply first fit, batch first memory allocation technique. These memory techniques called the external fragmentation. So there is a solution of external fragmentation. We should go for the compaction. So what is compaction, that we will discuss little bit after. So now I am coming on the compaction. Compaction is the process in which we combine the memory space that is scattered throughout the memory. We will combine that. So when we will combine, yeah, that means we can shift the memory from process from one memory location to another. That means we have to relocate the memory. So here we can understand more better with the help of an example. So this is the process 1, this is the process 3, and this is the process 5. Process P2 and P4 has left out from the memory, so there is a hole. Now, if we will shift the process P3 and P5 to the upward size, in that case, it is process 1, process 3, and process 5. So a combined space, this one, and this one is comes together, and that is used as a larger memory hole. Now a new process can accommodate in this space. So there is a technique, or this technique is known as the compaction in terms of the memory management. So here is the definition. Compaction is the process in which free space is collected in the large memory chunks to make some space available for the processes. In the memory management, swapping creates multiple fragments in the memory because the processes are moving in and out. Compaction refers to the combining of empty space together and processes. That means we are combining the processes, shifting one side and free memory hole one side. Compaction helps to solve the problem of fragmentation, but it requires too much CPU time because the CPU has to search out. Firstly, it has to take the data in the buffer. Then after it has to search where is the sufficient space. Then after shifting of the process, so it will be time consuming, and we can say CPU will not perform any useful task at that time. Now, coming on the techniques for non-continuous memory allocation. So there are two techniques. First one is the paging and second one is the segmentation. So we will discuss paging in this video, segmentation in the next video. Paging. Paging is a fixed site partitioning scheme. The basic method for implementation of paging involves breaking the physical memory into the fixed size of the blocks known as frames, and breaking the logical memory into the block of same size called pages. Means the physical memory, that means RAM, is divided into the equal size. Those chunks are known as the frames. So here is the physical memory. This is the physical memory. So this is the operating system. Now I am dividing this 1, 2, 3, and 4. 4 partition of equal size. So these are known as the frames. It is F1, F2, F3, and F4. There are 4 frames. The partitioning of the secondary memory is also known as the pages. So in general, as we know that the data resides in the hard disk, in the hard disk, whatever the data is there, we are also known as these are also known as the blocks or sometimes pages. Dividing the physical memory into fixed size of blocks is known as the frame, as we have discussed. The size is in between 512 bytes to 1892 bytes. Since the memory location is represented in terms of binary, that's why it is always in the power of 2. Sorry. Dividing the logical memory into the blocks of the same size is known as the pages. So CPU generates the logical address. CPU generates the logical address. So logical address is known as the divided into the pages, and physical memory is divided into the page frames. So CPU, whatever the address generated by the CPU is known as the pages, and the address representation in the physical memory is known as the frames. That means we have to map page into frame. Now, it should be noted the size of the frame and size of the page must be equal. So to run a program of size n, it needs n free frames. As I was discussing, the number of frames is the size of the frame is equal to the size of the page. So if the CPU requires 10 pages, so there should be 10 frames in the physical memory. Now, paging techniques. So as I have discussed in the previous video, CPU generates the logical address. That in that logical address a relocation register value is added, and then after we can find the physical memory address. Now, paging techniques. The CPU, as I have already discussed, CPU generates the logical address. Logical address is divided into two parts. First one is the page number and second one is the page offset. Similarly, the logical memory, the logical address, that is the address of the physical memory, uh, is the address contains frame number and offset. So there should be a mapping between the frame number to page number. How will it? Let us discuss. Suppose that CPU generates some address. So this address is in terms of the pages, page 0, page 1, page 2 and page 3. There is a mapping scheme. There is a mapping scheme that is known as the page table. Page table defines which page will reside on which frame. For example, page number 0 will reside as at frame number 1. Page number 1 will reside at frame number 4. Page number 2 will reside in frame number 3, and page number 3 will reside in frame number 7. So we can say it is the basically page number generated by the CPU, and corresponding to that it has to find out the frame number, and it can get the actual memory location. So here is the example. Suppose that CPU generate a logical address. As already explained, the logical address is divided into two parts. First one is the page number and page offset. So page will be searched into the page table, and we have to find out the page number, frame number. So once we have find out the frame number, then after the offset is added. Basically, frame number will provide the initial or the base address of that frame. Then after, a frame may contain 1000 or 100 instruction. I have to go on the instruction number of 532. So the base address will provide the number 500, and 32 will be treated as the offset and 32 will be treated as the offset. So we will add the offset number into the frame number and we will find the actual instruction that reside in the physical memory. Corresponding to every process, there should be a page table. Keep in mind, corresponding to sorry, corresponding to every process, there is a page table. So there should be a mapping for every process from page number to the frame number. For example, process is has the page table like this one. Page number 0 reside at the location frame number 0. Page number 1 reside at the frame number 1. Page number 2 at frame number 2. Page number 3 at frame number 3. Process B does not have the mapping. So its page number 0, 1 and 2 is shown as blank. Then after process C, page number 0, 1, 2 and 3 have the frame number 7, 8, 9 and 10 respectively and so on. So there should be a mapping between the page frame number to the page number or sorry from page number to the frame number. Here is a question. Suppose that a logical address space of 8 pages. Here 8 pages are given. Okay. So we should draw the logical memory space that has 8 pages. 1, 2, 1, 2, 3, 4, 5, 6, 7 and 8. Here is the 8 pages of each 1024 words. That means 02, 1023. Again 0 say 1024 to 2047 and so on is mapped into the physical memory of 32 frames. Here there are 32 frames. Okay, I am drawing 32 frames, something like that one. It is a 32 frame and here it will be OS also. So I cannot ignore it. So 0, 1, 2 and up to 31 total number of frames 32. Now question is how many bits are there in the physical address and the logical address. So how many bits must be there for the physical and logical. So let us check for the physical memory. As there are 8 pages, there are total number of logical memory has the 8 pages. So to represent 8, it requires the 3 bit because 2 to the power 3 is equal to 8. Now, and so 1, 2, 3, 4, 5, 6. That means it will be represented at 000. It will be represented at 001, 00010, 011 and so on. And last one is the 111. So total to represent the 8 pages, we require the 3 bits. Now, in the each page, there are 1024 words. That means it is just like the 1024 lines. So to represent the 1024 lines, we require the to the power 10. 1024 can be represented as to the power 10. That means 10 bits are required to represent the 1024 words. So total number of bits required in the logical address space, since it is generated by the CPU, it is equal to 13. Now, what's about the physical memory? There are 32 frames. To represent the 32 frames, we require the 5 bits because 2 to the power 5 is equal to 32. plus as I have already told you, the frame size is equal to the page size, or we can say vice versa, the page size is equal to the frame size. So this size is equal to this size. So it has the 1024 words. So it also contains the 1024 words. So again, to represent the 1024 words, it requires the 10 bits. So total number of bits required 5 plus 10, that means 15. So here to represent the physical address, we require the 15 bits, and to represent the logical address, we require the 13 bits. I hope it will be clear. It has been clear to you. Now, how to implement this? The hardware level implementation can be done with the help of the TL.B, translation look ahead buffer. So what is it? Let us discuss. As we know that the the page table should require an space. So where should it reside? We cannot put it into the secondary storage. We cannot put it into the registers. So where it should be? So it is in general kept in the main memory. That means the primary memory. And page table base register PTBR points the initial position of the page table. For example, this is the memory, and these are the spaces of basically frames, and page table for process P1 reside here. So a register PTBR will contain the address of the starting location of page table, and another register PRLR means page table length register indicate the size of the page table. It is just like the limit register as we have discussed earlier in the memory protection. So what will happen? The CPU will generate an address. So it will firstly search in the cache memory. Now, so TL.B can be implemented as an associative memory, that is very fast memory. So here there is a mapping for a page number corresponding to the frame number. When CPU generates an address, it is divided into two parts, page number and page offset. Now, this page number will be searched in the TL.B translation look ahead buffer. If it is found, then corresponding to that page number is searched for the frame number. Suppose that this is the page number 10 and corresponding to the frame number 31 is there in this. So 31, it will search for the 31, and then after 31 page number frame number is here. So it will go for the frame number 31. Now it will add the offset to find the particular instruction. Where is the actual location of the instruction in that frame? So offset value will be added. So this is the concept when there is a hit. Hit means when the page is found, page and corresponding to the that frame number is found in the TL.B. If suppose that it is not found, then this is known as the miss. Means we have not found, that means we have missed. When it has missed, so it will search for the page in the page table. So it will go into the physical memory, and in the physical memory it will search for the page table, and corresponding to that page table there will be a mapping from page table to the frame number. So it has to search the physical memory for frame number corresponding to the page number generated by the CPU. Then after, it will bring up that page into the TLB, that mapping into the TLB, and again execute the process. So this will continue until the page fault will not occur. What is the page fault? We will discuss little bit later. So here a flowchart is there. Search for TLB. Is required entry in the TLB? If yes, generate the physical address. This is the physical address. If not, access the page table. The page table residing in the main memory. Update the TLB means bring up that page and corresponding to that frame number into the TLB and generate the physical address. So this is the process to map a page number into the frame number. That means the address generated by the CPU into the physical memory location. Advantage of TLB. TLB reduces the effective access time because cache memory is much faster than the RAM or the secondary memory. Only one memory access is required when TLB hit occur. Yes. So once the hit is occurred means data is found in the TLB. So next address to search for the frame because page to frame mapping is there. TLB can hold the data only one process at a time. This is the one of the drawback because there may be number of processes executing simultaneously. That means concurrently one after another. So in the multi-programming environment, only one process data can reside in the TLB. Once execution of that process has been completed, it has to flush out and bring up the data for the another process into the TLB. After some process is running, after some time the running process when TLB hit increases, the process starts run smoothly and context switching occurs. Means from one process to another process. The entire content of the TLB is flushed. That means now I have to load the content of the another process. Then TLB again updated and with the currently running process. In this case, a special hardware involved. So there should be additional cost. Yes, because a TLB is added, a associative memory is added into the architecture. So extra cost must be there. So effective access time using the TLB. So first point, as I have discussed, there are two terms, hit and miss. If data is found in the memory, so it is known as the hit. If it is not found, then it is known as the miss. So X, if data is found in the TLB, that means hit, then after what will happen? If data is found here, so it has to search the data into the TLB. So firstly, the data may be reside the sorry the mapping reside at this location. So there is a time that may be in the nanosecond to search that mapping in the TLB. So there is required of some time. Then after it has to search for the particular frame number corresponding to that page number that is generated by the CPU. So TLB, if it is a hit, so access time of TLB to search the page in the TLB, then access time of the memory to map to find a corresponding to mapping a frame number into the physical memory. If it is a miss, if it is a miss, how I will come to know it is a miss? When I will scan the entire TLB and data is not found in the TLB, then it will be a miss. So time to access the TLB plus plus 2 into access time of main memory. Why it is 2? So let us go back. So firstly, it will search for the page table. It will search for the page table entry and corresponding to that page and frame mapping will be bring up here, the bringing time is almost negligible. Then after it will search for the frame, and then after once the frame is found, the date, the offset is added to that to find that particular instruction. So two time visit of the physical memory. First time for the page table and second time for the frame number. So there's two type of mapping. That's why here the 2 into access time of main memory. Let us consider it by example. That will be better one. A paging scheme uses the TLB. A TLB access take 10 nanoseconds. Means the searching time of the TLB is the maximum 10 nanosecond. In main memory takes 50 nanosecond. That means if data is not found in the TLB, then the searching will take 50 nanosecond. Or we can say if the data is found in the TLB corresponding to searching of corresponding frame number is also 50 nanosecond. The hit ratio is 90%, means there is a 90% chance the data will be found in the TLB. 10% not found in the TLB. So we will find the result as hit ratio. Hit means zero point 0.9. So TLB is the 90%, that means zero point 0.9. So miss will be 0.1. So hit multiply by time to access the TLB plus time to access the physical memory location. Why physical memory location? Because frame is existing in the physical memory. So 10 nanoseconds plus 50 nanoseconds. If data is not found in the TLB, then it is a miss. So zero point 0.1 multiply by 10 nanosecond, that means searching time of TLB plus 2 into time to access the physical memory, because physical memory is visited twicely. So it will be equal to 65 nanoseconds. So this is the concept of the hit and miss. So this is from my side about the fragmentation, paging, how to map a CPU generated logical address into the physical address and in numerical along with TLB, whether the data is in the TLB or not associated with the TLB, how it will be calculated. So I have completed from my side. Thank you.